All right, coming up, we have Code of Ethics on Thursday, so I'm going to talk about that today. I'll probably talk about it a little bit on Thursday. Prototype in what, a week and a half? So prototype 1 on the 13th. I'll talk about that more extensively on Thursday. Does not, I will say it does not have to be a complete prototype. It can be a prototype of a subsystem. Okay, so it doesn't have to be complete, the whole system. It's great if it is. The sooner you get to the whole system, the better, right? But it can be a subsystem. It does have to be functioning prototype. So throwing it together the night before is not going to work, or the hour before class, just so you know. If you have questions on prototype 1, don't hesitate to ask me, but maybe wait till Thursday because I'll talk about it in more detail. Okay? Any questions so far on that? Lots of stuff today. Prototype 2 is on the 27th. All right. Well, let's keep going. Today, we're going to talk about ethics. So engineering ethics. Why do we have them? What are they? How do they guide us? That kind of stuff. And then we're also going to talk about graphics. So I'm going to go through a little graphics lecture. Just because it's a big part of what we do as engineers, we communicate on paper. So first question to you, and giving you some notes for your notebook, is why do you think engineering ethics is important? We'll take 5 minutes to take some notes down. Why do you think engineering ethics, why would it be important? What do you think? Anyone want to offer up a suggestion while you're writing? Why would it be important?
Integrity in everything is crucial for just life in general to function.
Right. I agree.
Problems.
Why would it be important in engineering?
Because if you don't have integrity, then things fail, you know, that be snagged.
That's one of the perfect reasons. Is if we're not ethical, then that means we're unethical, and the things we do potentially could fail.
You'll always get messed up.
Right? What are the reasons? Anyone else have any other ideas? None?
Not be lazy.
Not be lazy? Yeah, to guide us. I think that's valid, right?
Yeah.
Like, to guide us is a great thing. I kind of added that to not be lazy, but yeah, it's the same reason we have like societal laws, right? It's why we have a speed limit in a car, to guide us.
So it's like,
Still our choice, right? Still our choice.
so they basically follow a code or a method, like rules.
Yeah, we're gonna go through the code of ethics, yep, that one of the societies has. Any other ideas on why is it important? Absolutely. Yeah, so all kinds of laws around like your rights of design, right? Your work. So again, to guide us. Absolutely, in a lot of different areas. All right, here's the big one. Money. Money is why we have a code of ethics. Currently, the cost of helping professionals act ethically is controlled by a number of agencies. And those agencies got developed because of unethical acts in the past. It's the same reason we have societal laws. We have a speed limit because some folks were driving way too fast when we didn't have a speed limit and killing themselves, right? So the reason we have ethics in engineering, a big part of it is money. Oh, it comes down to money. The Environmental Protection Agency, the EPA, that's a regulator, basically of ethics. They're saying, hey, be ethical when it comes to the environment, right? The Food and Drug Administration, really they're saying like, don't make bad drugs, people, right? Be ethical about your drug making and your drug delivery. OSHA, huge, 495 million a year to have OSHA. And what does OSHA do? Keeps us safe. Keeps us from ourselves, basically. Right? And it also guides engineers, it guides industries, it guides a lot of folks. Without this kind of guidance, we tend to get some unethical behavior. We still get it, but we get less. People get harmed. You guys mentioned that.
How do you spell OSHA?
Occupational Safety and Health, or it's OSHA. OSHA. Yeah. People get harmed by poor ethical decisions. That's a big one in engineering, a big one. A big part of our job is making those decisions all the time. At any level. So you don't have to be the lead design engineer to make a mistake. Any mistakes that get made along the way. Not that they're intentional, but if they're known and then not disclosed, that's unethical, right? So. All right, let's talk about ethics in general. Here's your next question to write some answers to for 5 minutes. On what basis should we make ethical decisions? How do you make ethical decisions? It's really, how do you make decisions, life decisions? What guides you to make a good ethical decision? We get them all the time, right? Like you're in the grocery store and you're checking out and you're walking out to your car and you realize that you didn't put the rack of soda pop up there and you didn't pay for it. Now what do? You have a decision to make. So what guides you on those decisions? I just did that, by the way, the other day. It was in the bottom of the cart and then pull it out and I didn't pay for it.
So what you do?
I can't tell you. I gotta let you write down what you would do. Yes, sir.
Yeah, to like it's. What am I gonna say? I'll tell you remember. I'll tell you.
We're just writing right now.
I just.
On what basis? What guides?
Oh, good question. Yeah. The basis of your conscience.
Oh, I don't want answers yet.
Oh,
I just want you to write.
okay. Sorry.
You're gonna influence me on what I write.
Okay, sorry.
What's today? Tuesday, right? February 4th. That should be on the piece of paper that you're writing if it's going into your notebook. Tuesday, February 4th. How many weeks? What week is this? Dang, you guys are on it. That's because you're all here. The ones that aren't here, they're not on it. It's all right. That's good, because 1 in 4 of you are gonna make it, so you all are the one so far. The other 4, they're not here. All right. Anyone want to offer up what guides you? Yeah,
Morality,
morality. So morality is, what is morality?
like doing the right thing.
Doing the right thing. So
doing
that
the
is
thing.
one of the ethical guidelines, is the difference between right and wrong, and knowing the difference and then letting that guide you. Yeah, morality is good. Yeah,
You should have a conscience that you develop.
yeah. That's it's a little bit on the same track. It's different. It's the difference between right and wrong. Yeah, absolutely. Religion guides us for sure. Morals, we just had that one. Good one, though. Aaron.
Responsibility to society,
Responsibility to,
to
yeah,
be part of it.
absolutely.
Kind of what I said, humanitarians, the greater good.
So you actually know the ethical codes. Well, you know one of them. Maybe you know them all. You probably know them better than me, because I'm no ethical expert as far as the codes.
Seeing people do dumb stuff.
Seeing people do
Like
dumb
if someone
stuff.
does something-
That's right and wrong.
Oh,
That's back to right and wrong. The law, that's actually a really good one. Yeah. So the law, like just knowing that this is the law and we're gonna follow that law. One of the ethical canons is very based on that. Excellent. So we got religion, we got right and wrong, we got utilitarianism, which, what was your definition of that?
I said humanitarian.
Humanitarian.
Greater good.
Okay, the greater good. That's one of them. All right. So here they are. There's 4 of them. And again, I'm no expert. I've not studied ethics deeply. When you get your 4-year degree, you'll take an ethics and engineering course that goes a little deeper than this. Some of those courses have gone away and they just blend it into the curriculum somewhere. Like you're getting it in GE101 a little bit, but it goes a lot deeper than that. So the first one is a cost benefit analysis. So you might think of it as risk reward, like, hey, what's the risk of me not returning this rack of soda pop that I didn't pay for? Like when I get to my car and I literally am putting it in my car, is there going to be a security guy that literally runs me down and tackles me, and like, that's the possible cost to doing an unethical act. So it's this cost benefit analysis on the first one. The second one is duty ethics, which is a little bit like the law, which Tori said. But where does duty ethics really become big? Are there any military folks in the room? So when you're in the military, it is your duty to do a lot, and that is not something you question, right? That is your code and you do it. So duty ethics is a little bit like our laws. It is our duty to follow those laws, and it's our duty to do what we're told in those environments. Then there's rights ethics, and that one emphasizes that we all have moral rights, morality. The issue I have with this is morality is very independent. It's very individual, right? My morality might be different than your morality, might be different than somebody else's. So that's a tough one for me. But it definitely guides you. Yeah.
I just had a probably pretty deep thought that that one point of duty can have a lot to do with preemptive, to be proactive, do something ahead to avoid
Yep.
problems. It's more to do with that than anything.
Absolutely. And the last one is virtue ethics. Regards actions as right that manifest good character traits. Regards actions as bad that display bad character traits. Again, it's got to be defined, right? What's a good character trait? Like, it's got to be defined. So it can go a lot deeper than just this discussion, that's for sure. And it focuses on the type of person we should strive to be. But I'll talk about that quite a bit during this class, because I do think engineers should strive to be a certain kind of person. No way, I'm not moving. This is my spot.
Oh, okay.
All right, is that better?
Yes.
I can go to the back of the room.
Oh, yeah, that'd be nice.
Questions? The good news is you don't just use one, you can use them all, right? You use different ones at different times, but you should be aware of them. Like you should be aware of thinking about your thinking, right? That's called metacognition. When you think about how you think. So it's a good thing to do now and then, to just debrief yourself on ethical situations and how you handled it and how you want to handle it in the future, kind of thing. You get a fair number of them in engineering. Anytime you're in industry, you're going to get a number of ethical issues that you just see, right? If you see things and you got to decide whether you're going to bring that thing up that you see or whether you're not going to bring that thing up. That happens a lot. So you have to decide kind of early on. This just says you don't have to choose. Which ethical theories should I use? Use all the theories. I think we're going to go to canons next. Yeah. So there's most professional organizations have a code of ethics, or they're called canons. The National Society for Professional Engineers has canons. The Institute for Electrical and Electronic Engineers, IEEE, it's called. They have canons. American Society of Mechanical Engineers has canons. American Society of Civil Engineers has its own code of ethics. You can look them all up, and you should, before you build your own code of ethics for your team. Because I want those code of ethics to be really engineerish, right? But also I want them to be for your team. So with that said, you should definitely do research when you write your own code and use them. Like if you see one, it's like, yeah, let's do that one. Let's have that one in our code of ethics. So it's not difficult to write your code of ethics. You can do a little bit of research, get a nice list, decide the ones that you want to adopt as a team, and put it in your code of ethics. This is the IEEE code of ethics. So we'll just give you an example. So the first one, to accept responsibility in making decisions consistent with the safety, health, and welfare of the public, and to disclose promptly factors that might endanger the public or the environment. So basically it says make good decisions. Canon 1 says make good decisions that are focused on safety, health, and welfare of the public, right? And then anything you see, disclose it. So that's the first canon. Second one, to avoid real or perceived conflicts of interest whenever possible, and just disclose them to affected parties when they do exist. So, anyone have an example of conflict of interest? What is conflict of interest?
The only thing that can come to mind is like, if you have a project that you're working on and your estimation is that you need certain amount of products or certain things, and they may be expensive, but then your bosses say, no, you only have this limit of funds, so there's like a conflict of interest.
Yeah, it's close. It's a little different. Conflict of interest is going to include bias.
Include what?
Bias. So the best example that I think you can wrap your head around, as engineers, you will deal with vendors, people that want to sell you things. Those folks that want to sell you things will also want to befriend you. They'll offer, hey, we should go golfing next weekend. I am at a private country club. Would you like to come along? Sure. That sounds fun, right? So now we become friends outside of work, yet this person is trying to sell me stuff for the company. But so are other people trying to sell me stuff, right? But they're not taking me golfing every week. So that's a clear conflict of interest because it involves bias. Right? So they're all around, like people, especially with vendors. Vendors are the worst, you know, they'll, my first week I was offered Blazer tickets in box seats, like, come on, you should come out with us, man. But that person was trying to sell his product, right? He was taking all the, bunch of engineers were going with him too. I'm like, why am I not going? Like, holy crap, what do I do? Like, that was like in the first week. Like, geez. Anyway, so yeah, it's out there for sure. Third canon, to be honest and realistic in stating claims or estimates based on available data. So we run a lot of numbers and we do a lot of estimating. And when we're unsure, when the numbers are not clear and we're unsure with our work, we just need to be honest about that. That's huge. So we can't be over egotistical. We can't be overconfident. It's just, it's not going to end well, right? Especially when you know inside of you that you don't have the numbers to make this decision as solid as other folks wanted you to make that decision. So you have to be able to just be honest when it comes to data and your calculations and those kind of things.
I have a good question. It says reject bribery in all its forms.
That's the next one.
Would it, oh,
Yeah.
well, I thought it had to do with the
No,
the
see, this-
vendors.
These numbers are kind of.
Yeah, well, I mean,
This
it
is the
still, it
next
still
one.
relates to the vendors where you said you.
Oh, yeah, absolutely.
What I was gonna say is,
Absolutely.
what I would probably attempt to do is say, yeah, I will take your tickets, but you need to understand that we will not, you know, be persuaded by any kind of
Yeah.
bribery. Or
Yeah,
any-
there's a few things going on there though, because it may look different to others. You taking the tickets and going,
I would
you
just
know.
make it clear, I'm like taking it for that, I'm not.
Yeah, but it's hard to make clear to others,
Oh,
others that are seeing this happen.
so you have like.
Other vendors that see it happen, you know, if they
Some
find
sign
out.
it Thing
Yeah.
that says no or not.
It would be better just to not do it.
Yeah, I agree.
Reject bribery in all forms, that seems pretty straightforward. Don't get bribed, right? To improve the understanding of technology. This is a great one. I love this one. To improve the understanding of technology, its appropriate application and potential consequences. So they have a canon that says your job is to improve technology as you use it, whatever technology you're using, and make sure it's appropriate. They keep going. 6, to maintain and improve our technical competence. So this canon is focused on us, that we maintain our technical competence in whatever we're doing, right? If I was still at Kiewit, still making conveyors, I need to make sure that I'm continuing to educate myself on conveyor safety, like what are the last conveyor accidents that were out there and why they happen, and am I about to commit that same kind of accident? So. Seven, to seek, accept, and offer honest criticism of technical work, to acknowledge and correct errors, to credit properly the contributions of others. At this point, I kind of feel like the canons start to like line themselves up with lawsuits. Like, oh, there must have been a lawsuit at some point where somebody took responsibility for somebody else's work, which happens, right? Shouldn't happen, but it does. And, you know, it wasn't acknowledged.
Just gonna say that, OSHA earlier. It's a advantage of
Oh, absolutely.
the State rules. are written.
Yep. Yep, that's how it got developed. Lawsuits, for sure. And this is one of the original canons too. To treat all people fairly. Way ahead of its time. Regardless of such factors as race, religion, gender, disability, age, national origin. It's been there forever, that canon. In most of the engineering ethics. So that's kind of fun. Obviously, to avoid injuring others. Number 9, their property, reputation, or employment by false or malicious actions. I think that comes from blaming other people, right? For mistakes maybe that an individual made. Yeah.
I definitely have some good input on this, since my experience of working out there in the industry, with CAD and even in assembly lines. They have a lot of those safety things, put in place. And
Absolutely.
they have the lockout things, and
Yeah.
I've seen times where they don't completely put all the locks on, or people will open those things, and it
Yep.
just, it's always big risk and always creates trouble, so people really.
Yeah, no, there's dangerous stuff out where you're gonna work. So especially if you're in a manufacturing facility, a lot of dangerous equipment, dangerous chemicals, dangerous air, all of that kind of stuff. So you have to be super aware of your environment where you're working.
People get lazy.
Yeah. And number 10, to assist colleagues and coworkers in their professional development. So that's one of the canons, is to help each other. To assist colleagues and coworkers in their professional development and support them in following this code of ethics. So this is just IEEE. When you look at American Society of Mechanical Engineers or Civil Engineers, it'll be similar. I mean, really, they're just telling you to be a good human, but I guess we need to write it down. It's important. You have the code of ethics to do. It's supposed to be a 10-point code of ethics. Again, you can look at code of ethics and steal them if you want. I would encourage you not to steal them word for word, customize them for your team. But the whole team is going to agree to this code of ethics. So you can add things like, one of our code of ethics is to show up, to meetings on time. So you can have really simple ones in your team's code of ethics, or, to do your share, to be as focused as you want, kind of thing. I'll use the code of ethics in the end because you'll do a peer evaluation on your team. So your team's going to evaluate your behavior very much like we do in engineering teams. Guess what? Sometimes it's every 6 months you get evaluated. Sometimes it's every year you get evaluated, depending on if you're a new hire or been there a while. It can even be more often than that. And that evaluation is sitting down with your supervisor and talking about how you're working within the team. Because your supervisor knows how you're working within the team, and they can get feedback from the folks you're working with. That's what they do. So this is what we do in industry, and this is what you'll do in this class, is you will evaluate your teammates. And I have a way to do that. It's private. You'll write it up and submit it. I have the code of ethics that I'll follow and ask you about. But it'll really be like, did they work hard? Did they do their share? Did they do what they said they're going to do? All of those basic things we're supposed to do. But that's just a heads up. That's one of the ways I evaluate how the team functioned and who did what. Because I don't know, right? I'm not in your team meetings, and I'm not building prototype 1 with you. So I have to have some way to do it in the end. So that's just fair warning that that's happening in the end. And I use your team code of ethics kind of as my guide. So questions? Sound good? Good and reasonable? Thanks. Okay. Let's do the 6th, which is Thursday. So you get Thursday lab to do it. But it's due on Thursday. And so I think I got all the schedules except for one team. So some team missed the schedule submission, which was due yesterday. So again, it's hard to keep track of stuff. I'm sure that team did a schedule, it just didn't get submitted. Okay. So keep track of stuff, however you got to do it, because things are happening. It's busy, very busy. I'm pretty sure this is the only class you have too. And you don't have any work lives and you don't have any home lives, so
Yeah, right.
we're good. You're focused on GE 101. All right, let's talk about graphics. Graphics, graphics, graphics. Here's my graphics example. It's chaos. But this is what we get to learn and learn how to read, learn how to decipher it. Anyone know what that is? Got any wrench heads in the room? Yeah, what is it?
It's a piston rod.
Blueprint for sure. Piston rod.
Oh, with the.
Yeah, what is that? What is that thing?
Oh, yeah.
Right? Cool. Not really, not unless you're a gear, I'm not an engine person, right?
You never.
It looks like chaos. Anyone know what these are?
Bolts.
I know, they're kind of small.
Oh, they're the side, the cross section views. Of the piston rod cross section, probably of certain things.
Yeah, they're section views. They're the cross section of it, right? So graphics gets super complicated. The number one thing in your graphics you want to look for is clarity, and that's not it. This is not a great example of clarity, which is why I use it. Like this could be much more clear and just less information is better sometimes. No need to save paper this day and age. Okay. All right, so let's talk about graphics in general. 4 things that really I'm going to focus on: clarity, accuracy, completeness, which means we need full shape description, right? This is not a graphics class, but you have to do a little graphics on your project. So this is where I give you kind of the basic nuts and bolts. And in the end, we really don't want the reader or the user of the drawing to have to do math. So if you're trying to decide, should I put this dimension in or not put that dimension in? If somebody has to do math to figure it out, that's our job as the engineer. So no math required for the reader. All right. We're getting there. Remember, the PowerPoints are on Blackboard.
I know.
You can print them or you can digest them later. I know I go fast. Everyone goes fast. All your teachers go
Yeah.
fast, probably.
You're right.
So I try to give you the content so you don't have to write it, right, word for word. I would jot some notes down, but you don't have to get it word for word. Anybody know what those are? Yeah, they're scales. So there's all different kinds of scales, and I got a bunch of them. So if you need to use the scale, they're over here in this box.
Guess we know this.
The 2 common kinds of scales are architectural and decimal. So engineers tend to use decimal scales. And that's this one, engineer's scale. It's broke up in tenths. So that 1 inch has 10 spaces, tenths of an inch. Okay. So that's a 1/2 inch, right? That's 1/10, that's 2/10, that's 3/10. That's how an engineering scale broke down. The civil industry uses both engineer scale and what we call an architect scale down here. So the architect scale is not 10s, is it? There's a lot more than 10. How many are there? Little ones. 16 of them. Yeah, so it's 16ths, 8ths, quarters, and halves of an inch. So just 2 different scales. And then there's a few other ones, right? There's metric scales. But we use these things quite a bit because objects don't typically fit on paper, right? Objects are most of the time bigger than paper. So we have to be able to scale things down to get it onto the paper, and then we need to be able to understand scale. So that's one of the things I want to try and make sure that we all understand before I go much further, is just basically scale reduction. Right? So this is A size paper, 8.5 by 11, or letter is what we call it, right? A size. B size, Cassidy, hold up that big piece of paper. B size is this thing, 11 by 17. C size is even bigger, but we don't use it much anymore. And then there's D size, like that's a plotter back in the corner. And that'll go up to D size. That's back in the day when we could do big drawings. Now, almost every organization has said, we don't want your big drawings. We don't want to store those damn things. They're huge. Where do you put them? Don't do it anymore. So B size is as big as the county will take anymore. No bigger than B. So that means we got to reduce even smaller, right? Because we got to get into B size or even smaller onto A size. So these will scale things for you. They literally will scale them for you. Because there's the 10 scale, right? And there's also a 30 scale, which means there's 30 increments per inch, right? If I use the 10 scale and I measure an inch, I get a full inch. Does that make sense? I mean, it's a normal scale. But if I measure an inch on the 30 scale, that's right here. Focus, right? It's 3 times smaller because there's 30 increments per inch instead of 10 increments per inch. 1/3 scale. That's what the 3 would mean. Now, I really wish they would have put 1/3 scale, but they didn't. They put 30. So we have to be smart enough to go, oh, that's 30 increments per inch. Okay. And that's counting these 0, 1, 2. These, if I flip it over, I can run it the other direction and get even longer kind of thing. But there's also like 60 scale. Wow. Can you even see those? I can't.
No.
Yeah, they're so small. Yeah, so that's a 6 times reduction. So these will reduce for you. What's nice is you don't have to do any math. You just need to read the new scale and mark it. Like 1 inch on the 60 scale is that first long one right there. So there's 0, there's 4, 1, 2, 3, 4. So it's that one. That's 1 inch. Pretty tiny. And good luck reading the little ones in between. That's really small. That's smaller than the width of your pencil lead, which is what we use these with, is the pencil, right? So these will do up to 6 times reduction without us having to do math, just by reading the scale. Does that make sense? Okay, so they're super handy up to 6 times, but what if we need to do like 100 times reduction? Well, it's not gonna work. This only goes to 6. 100 times, it's gonna require this. Okay. So an example of scaling is if we were gonna draw, I don't know what it is, but I'm gonna make it 60 inches long and 10 inches tall. So whatever that is, in real life, it's 60 inches long and 10 inches tall, okay? But I'm gonna get it onto this piece of paper. So I have to figure out what my scale is. Right? I have to figure this out ahead of time before I draw it on the piece of paper. So how do I do that? How do I figure out how to get 60 onto this piece of paper? How many times do I need to reduce it?
Oh, you asked.
We could guess.
Yeah.
Right, we could guess like, oh, what would 6 times reduction be? So then we divide by 6, right? We take 60, divide by 6, and what would it be on my piece of paper? 10 inches. How big's my paper? 11. That's gonna be pretty tight. No room for dimensioning. No room for notes. It's gonna just hog the whole thing up. Right? So 6 isn't gonna work. How do I figure it out? I figure out my usable space of the paper. So however much usable space I want to use. Like, even this is too big. Like, I think I want it like from here to here on my paper,
About half.
right? So let's see, that's about 4 inches. So I want the 60 to become, I want it to fit in 4 inches. Right? Does that make sense?
Yeah.
So far, so good? So how do I figure that out? Like, oh, how many times do I have to reduce it to get to 4 inches? What if I just take the 60 right? If I want 4, I mean, I could write an equation. We are engineers, right? If I want it to equal 4 inches, what do I gotta do with the 60? I gotta divide by something. Right? So what do I gotta divide by? Yeah, let's just look. If I solve that, how do I solve it?
16 divided by 4. right?
Yeah, we all got the algebra down, right?
Which is, you know,
We got the algebra down. So x equals 15. 15 times reduction to get it onto this piece of paper in this amount of space. Is that okay? Everyone's got that math level, right? That's how you figure it out. You figure out like, well, how much space do I have available on my paper? And I gotta get this thing to there, set up my little equation, or just do the division. And you'll get your scale factor, right? So how do I draw it? Well, every number gets divided by 15. So 60 divided by 15 is 4. So then I can take my ruler at the 10 scale and draw 4 inches. Right? And then when I dimension it 60 inches with my fancy dimensioning. How tall would it be? Uh, 10 divided by 4, which is 2.5. Make sense? So 2.5.
Yeah.
There it is. Now I've just drawn it to scale, and then what dimension do I put here? 10. You do not put the scale size down, you put the real size. They're gonna make it to this size. You're just trying to get it onto the paper.
Is that right though? Wouldn't it be, actually end up being 10 divided by 15?
Yeah, I was waiting for you to say, like, look at, this doesn't look right, does it? 60 and 10? Ah. Everything gets divided by your scale factor.
Yeah, 0.6666.
Yeah, thank you. Perfect example of why we work in pencil.
I threw myself off. Wait a minute, that's right.
Everyone else just bought in. It's all right. How much is it?
I think it's 1.3.
0.6666.
0.6 is right here.
Yeah, 0.666.
Oh, man. Anybody got a calculator? Any engineers in the room?
0.666.
Any engineers in the room?
0.667. 0.67.
I need a confirmation. Thank you.
0.667 or.
So there's 0.5, there's 6. Where's 6.6? It's in there somewhere. So that's manual drawing for sure. In there somewhere. Doesn't really matter, right? Because they're gonna build it to the dimension you put down. They're not gonna build it to the size you drew it.
Yeah.
That looks much better. Great job, people. That is scaling.
Should have went with my confidence.
Okay. The last piece, this is not good enough. Like, this is great. We got on the paper. In the title block or in the information area, I'm not gonna go deep into title blocks. There should be scale. You see that? Yeah. And what would the scale be? 1, 2, 15. The number that we're dividing by over and over and over. As soon as you figure out your scale, write it down. Because you'll forget the next day, like, what scale was I using? What the hell? And then you'll flop the wrong scale down and you'll start working for an hour and realize, oh, I just drew that whole thing to a different scale. All right, excellent.
That's why we didn't get the.
Questions?
We didn't get the scale.
Scaling. Super important that you get that concept down. When you go to AutoCAD, you're going to be scaling stuff all the time. It's great. AutoCAD can do all kinds of changes quickly. But if you don't have your scale down, you're going to muck it up because you've got to understand the scale that you're working in layout so you can get the model space scale correctly and yada, yada, yada. All right, excellent. Let's just talk about graphics in general. One of the common graphics that are used is this glass box theory, because we take three-dimensional objects and we draw them two-dimensionally. Right? And we have a standard for that. We all do it the same. Thank goodness, or else we'd be getting this kind of crazy drawings from people, right? But when I get a drawing from another engineer, I understand it because they've done a front view, a top view, a side view. They've done sections, they've done revolved sections or half sections or quarter sections, breakaway sections. So all these different things that we learn when we go through graphics class, right? But there's a standard to it. So when you have an object and you're going to draw it two-dimensionally, which is typically what we do, is two-dimensional drawings, like like that, right? Front view, side view, top view. It's the basics. Take your object, put it in a glass box. All of the edges project to make visible lines. So all of these edges you can see project to make visible lines, and that's a continuous line, like a normal line. If you drew a line, you're basically drawing a continuous line. And that represents edges you can see from that view. So we have to be able to look at objects like from all different views. From this view, it looks like a rectangle. From this view, it looks like a circle. And from this view, it looks like a rectangle. This view, the side view, and the top view look exactly the same. So don't draw them both, but they look exactly the same. Just two is fine.
You have
Right.
the same dimension.
But then there's this view, maybe the front view, and it's very circular. So we have to be able to take an object and look at it like from all these different positions. And that's what we draw. So the glass box unfolds and looks like this. Right? These are the primary views, front, side, and top. Primary views. These are used less, left side, bottom. And then there's auxiliary views that could be at an angle. Okay. So just remember, you're representing the object, individual views. So when you do the front view, you're really just focused on the front view. Like, what can I see, right? What can I see from the front view? I see this surface. I see this surface. I see this surface, but it is slanted away, right? So it is not true size and shape. So that's the other thing we think about is, oh, this surface right here, that's not true size. That's slanted away from me, right? So I'm not going to dimension this because it's not true size and shape. I just want to dimension the true size and shape stuff. Things that we can't see, like the right side view, hidden. So in this right side view, looking from here, I see this surface, but I don't see the hole. So it shows up as hidden lines. Make sense? Yeah. Unfold it and you have your three views, front, right side, and top. Notice they're in projection. Projection means that one edge projects to another edge. This left edge projects to the left edge of the top view. They're in line with each other. Does that make sense? And the bottom projects, that's what these little lines are. They're projection lines. We don't draw them, but we put views in projection. It helps you draw them. Like when you put the circle here, you can literally just take a straight edge and come over and say, up, the dotted line is right there. It projects over to the view. And the bottom of the circle projects over to the view right there. So one view helps you draw another view. If you have it in projection, if you put it all wonky in some weird spot, then you can't use it. So keep them in projection. Yeah.
Yeah, I was gonna even say with, once you get into CAD, the projections are real helpful. So you bang out.
Oh,
those
for
circuit
sure.
views.
Yeah, construction lines like crazy. Questions on that? You have a homework assignment, which is to create a 3-view drawing of an object. Yeah, super fun. It's this object, right? We're running out of time, so I'm now cruising. It's this object right here, and I made copies for you. It's over here by Cassidy. Don't get them yet. But you're going to take this object. Oh no, this is your practice one. That's the one you're doing. That's the one you're doing.
Which one do we really do?
You're gonna really do which one? Number 9. Right there. Oh, yeah. So ignore the red. That's just to fake you out. Right? It's number 9. Here.
Ah,
So how do you tell how big it is?
Scale.
It's got little squares, right? Oh, you've had these before.
Oh, okay.
It's got little squares, right? Little grids. And then how big is the grid? Yeah, 4 inches by 4 inches. Is that okay? So like on this right side. Yeah, let's look at the little squares. On the right side, there's how many? 1, 2, 3, 4, 5 of them. So how far is the right side?
20 inch.
20. 1, 2, 3, 4, 5, 6. How far is this one? 6 times 4?
32. Wait, no, 6 times 4.
6 times 4.
Oh, yeah, that's right.
Oh my God, you guys are killing me here. All right. Math test on Thursday, I guess.
Yeah.
All right, that's how you tell how big it is, right?
That's why I got to calculate.
You're gonna draw the front view. That arrow represents the front view. The right side view and the top view, you're gonna draw them all in projections. No. On paper. Only once though, and then if you have to do anything else, like on your project, you can do it again. Easton.
Is it R right or the object's right?
Is what?
Is it R right from where we're looking at it, or is it the object's right?
It's always so you position yourself in the front. So this means front. Right? And then right is to the right. It's that.
All right.
Does that make sense? Yeah. The good news is in real life, you get to choose. Like this doesn't, what's the front view? Well, I get to choose, right? Your front view should be the most descriptive. So this would be your front view. That would be your side view.
Does that little triangle thing run?
Great question. Does the little cut, the slot, does it run all the way through?
Oh, yeah, that's good.
So here's the rule in engineering. If it's not noted, it goes through.
Yeah.
They would have to note it if it had a depth to it, right? So like, these notches clearly go all the way through. This one though, right here, goes all the way through unless it's noted. That's the only thing we can do is send it through. So yeah, all the way through. Tori, nothing. All right, so I did not make a copy of this, sorry, but I can print it right now. But I'll make, huh?
Yeah, because it's got more detail.
Review, yeah, front, top and side of object 9, yeah. But I'll print it right now. If you want a copy, you can hang around. We're out of time.
Is it on Blackboard?
Yeah, it is on Blackboard for sure.